Yeah, thank you very much. So what I'll be talking about is how to generalize something called synchronization engineering. And so with this beyond synchronization engineering, we mean that we generalize this method of controlling oscillators by allowing for non-pairwise interactions in something we'll call target phase model. But I'll explain all of these things in detail. So first, a look at the motivation. So why would you want to control coupled oscillators? And then, because this method, it really relies on being able to do a phase reduction, I'll introduce some preliminaries, some things you need to do a phase reduction. And after that, we actually go into what synchronization engineering is and then how we are generalizing this. So there's a lot of different systems you can consider as compound oscillators. So these are things like pacemaker cells in the heart or metabolic synchron U cells, or also things like power grid networks where Song Yu was talking about before. Then all of these, they can be more or less divided into two types of coupled oscillator systems. So there are, for example, the power grids. There's a type of system of oscillators that you could say that the network is more or less fixed, at least in classical power grids. But now it seems that there is some new types, which is not the case. But so we can control these, how these oscillators respond to perturbations, but it's a bit more difficult to try and control the whole network. And then there's these oscillators systems where it is actually possible to apply some kind of global feedback signal to them. And it's a lot more difficult to change the internal dynamics of these oscillators. So this would be something like biological systems. And this would be something like power grids that already exists. And these power grids, we're not looking at how to control them because there's better methods for that. But we're looking at these biological systems or just in general systems where you can apply some kind of global feedback signal. So in case of, for example, neurons, you might want to control this whole region of neurons by applying electric pulses to them. And so we're looking at how to make these kind of pulses very efficient so that they don't have to be too strong. You don't, for example, destroy neurons that you don't want to destroy. Actually, you don't want to destroy any, preferably. So what we'll do is do something called phase reduction. And I'll just look at the scheme now, but I'll go into detail about what all of this means. And to do a phase reduction, we'll need some things, the waveform and phase response curve, which I'll explain later. And then we'll want to compare a phase reduction to something called a phase model. And we actually want to do that when we have applied feedback to a population of oscillators, which still depends on some parameters. And then we do the phase reduction when those parameters are also there, and then compare this whole phase reduction to some kind of phase model that has some target behavior, some behavior we want to introduce into this population of oscillators. And by doing that comparison, we can determine what parameters we need for this to be approximately equal. And then we go back to the phase to the original system and put those parameters in and hope that we get the behavior that we wanted in our target phase model. And yeah, it's here that we want to allow for phase models with non-pairwise interaction, or cyclical, as Caro called it before. Yeah, so some preliminaries. A periodic orbit is a type of solution that keeps repeating itself in time. And then an oscillator is a dynamical system that has a stable such periodic orbit. And the aim that we have is to design some weak coupling between identical oscillators such that we can engineer their global behavior. And it should be weak coupling because we basically want the oscillator to not be thrown out of its cycle too much. And in proper terms, it should be that. So we want it to stay within the basin of attraction. Just if we wait long enough, it should go back to its normal oscillation after perturbing it a bit, applying some feedback. So if you have an oscillator, it can have quite, say, strange paths. Maybe it has a path like this and it's going around. But we can always map such a path to just the unit circle. And then we can map any point on the unit circle to some phase. So usually it's between 0 and then we go around and then we go to 2 pi and keep going like this. So when doing a phase reduction, you're reducing any kind of oscillation to just its phase. But then the question is, what do we do when we kick the oscillator? So what is the phase when it's not on the limit cycle? So we need to think how to do it, or actually people have thought about how to do it. So there is something that's called asymptotic phase. So when you consider an oscillator with some periodic orbit, so it's going around, in this case it's just on a circle, then for each point in its basin of attraction, so a point close enough to the limit cycle, there exists some unique function, some function phi, that for every x that you put in there, it will give, so every trajectory, it will give the phase corresponding to that point. And it is actually the solution of this limit. So if you look at the limit between some trajectory from a point x and the difference between the trajectory that starts on the limit cycle, and if they end up in the same point, or the limit ends up in the same point, then you'd say that they have the same phase. So in this case, it might be that after we kick it, and after a very, very long time, they end up like this. So in this case, there is actually a phase difference between these two after a very long time. So these 2 points, they would not have the same asymptotic phase. But you can find a point that also started on this limit cycle, or that started on a limit cycle, and that will, after a very long time, end up at the same place as this one. And when that's the case, then you find its asymptotic phase because it would be the same as the phase of that point. So what you can then do is actually draw a line through all the points that have the same asymptotic phase. And this is just, in case of a Andronov oscillator, it will look like this. And all of these lines, these are points that have the same phase. So if you, for example, would have a point here, and it would be kicked in the x direction, positive x direction, should be a straight arrow, but then you would see that it would stay on this isochron. So you can kick it, but it will not change its phase. So when you make, so when you reduce a system, a full system, to its phase reduction, you would have to scale the perturbation you're making. You have to multiply it by 0 because it's not changing the phase, even though you're changing x. And when you're here, it's the same. If you kick it that way, it's not going to change the phase. But then when you're, for example, on this point, and you kick it in that direction, you are changing the phase. And the oscillator, it's going, if it was going this way around, it would go backwards in phase, and in this case, it would go forward in phase. So you need, what we're using is a phase response curve, which basically maps how much it's changing depending on where you are in its oscillation when you give a perturbation. So this is just another example. It's a Brusselator oscillator where there's mapped out all these isochrons. And in this case, then the waveform of the oscillator is the first thing actually we need for this method, which is just the x coordinate versus the phase. And then the other thing we need is the phase response curve, which is what I just explained. So here at this phase is not changing. A perturbation in the x direction is not changing the phase, and here it's not either. And in all of this area, it's changing the phase forward, and here it's going backwards. So yeah, these are the two things, the waveform and the phase response curve, that we need from the oscillators. And actually this method can be applied to any oscillator where you know these two and where you can apply some global feedback in some way. Yeah, so that's the phase reduction. And this is just phase reduction in equations. So here we have some oscillator. And if we just do a phase reduction when there's no feedback and nothing happening, then it would just reduce to the frequency of the oscillator. And if we then add some kind of feedback here, then we need to scale it. So this epsilon is just something very small. Because we want it to stay in the Bayesian of attraction of the oscillator. But if we need to scale it, we use this phase response curve to scale the feedback. And now the form of the feedback will apply, or actually is applied in the original synchronization engineering. It's similar to, for example, Kuramoto model. So it's a summation. So we're taking information from one other oscillator at a time, putting it into some function that we'll look at later, what it looks like, and then just take a sum. So each time we decide, just based on information from one other oscillator, if it's going to put this current oscillator forward or backward. And that's it. And then we scale this and we use the waveform here to convert the phase into something the function can take in. And it's just normalized. So this is where we are. And now we look at the form of this feedback. Oh, actually, so one thing we need to compare it to a phase model. So we do some averaging, which is, yeah, it's rewriting what we have here so that we can look at this interaction function. And so we can just change the interaction function and then we will find different parameters. And here's just a relation between these things we already have. So the feedback, the phase response curve, and then the interaction function, you can fill in what you want. And this is the relation between the Fourier coefficients of them. So yeah, this is the feedback that is used by the synchronization engineering now. So it's just a summation, it's adding up different orders. So we have this gain parameter, which is determining the strength of each of these terms. And so we're taking information from some other oscillator at a delay. And then this is just the first Fourier coefficient, just for easy notation, I guess. And then we are doing this to the first power and the second and the third, and then depending on what your interaction function looks like, interaction function, I don't know where that function looks like, you would want more of these terms in order to match it well enough so you can find parameters for which this is actually true, for which this relation holds. So yeah, that's it. And what you do is you put your interaction function in there, solve these equations, and then you can find your gain and delay parameters that way. And now what we're doing is generalizing it. So before there was a function g that could take only information from one oscillator. So xi, I think it's setting j, but from one other oscillator. And now we're saying, okay, we can take information from two other oscillators. We put it into some function, and then we decide what to do, whether to go forward, go backward. And then we do it for all different pairs of oscillators or triples. And, in this case, it's just pairs. And then we see, yeah, what behavior we get, and also then this interaction function is then also, it's allowed to take information from one oscillator pair here, and this is just itself, and another oscillator pair there. So yeah, it gives a lot of opportunity to control for different kinds of target phase models. And then you just need to solve this equation, or these equations actually. So this is what the feedback looks like that we're proposing now. It still looks similar in a way. So here you have the gain parameters, and here there's a delay parameter, and here there's another one. And now you still have terms in case where it is this P or this Q are 0. Then you would have a pairwise, or a term matching the pairwise part of this phase model. But you also have mixed terms. So where P is not 0 and Q is not 0 either, then you have information coming from one oscillator and coming from another oscillator. And then being multiplied together, it's combined somehow, and then it's determining what's how to contribute to this oscillator. And so you have a lot more opportunities here to match these different phase models. And that's it. So synchronization engineering, it's some general framework based on phase models to construct this nonlinear delayed, time-delayed feedback to control any system of oscillators. And any system is a system where you can find a waveform in the phase response curve. And then beyond synchronization engineering, we are allowing for these non-pairwise or cyclical interactions. And the next thing is to verify all of this numerically. Yeah, that's it. Thank you. Thank you very much.
So, well, thank you for that talk. Do we have some questions from the... I don't see any new ones. So we have a few minutes. So you mentioned in your abstract about the epilepsy application of this. Can you say maybe a little bit more on
Yeah, so the idea is that in case of epilepsy, you want to control this, you want to break up these elliptic waves. And what you don't want is to, so what is happening quite a lot now in case of epilepsy or Parkinson is that they are applying electrical signals, but it's not always, so it can be that it is also destroying some neurons. And so it can be useful if you know exactly when or and what places you need to apply these electrical currents, electrical stimulus, instead of hoping for the best, I would say. And it could be, at least there's some evidence that these non-pairwise interactions are actually responsible for the propagation of for example, epileptic seizures in the brain. So it might be that in this way, so it's given that you can get this information, this waveform and this phase response curve accurately enough, then you could in this way design the feedback such that you are breaking up these seizures without doing too much harm. Because unless it's actually very, very bad for the patient, they are doing this. And it's a last resort, usually. And it could be really nice if you know it well enough to actually do this without impacting too many cells. So that's why it's just a case where it could be very useful to know how to apply the feedback, how to design it.
Thank you.